Hey there! So we have our data transformed. We have this nice facts and dimensions ready inside our data lake. Great, this data is pure, it's pristine, it's ready to be used. But how do we serve it to our consumers? It is available in a data lake. And not every consumer out there, not every solution is able to connect to a data lake and read data stored in a Delta format. So what then? How to handle this? And solution is to add yet another component to our design, this relational data warehouse that will solve this issue. And the service that we are going to achieve this is again Synapse Analytics, namely dedicated SQL Pool inside this. So let's get started. Alright, so the topic for today is dedicated SQL Pool inside Azure Synapse Analytics. But before we jump into details, let me remind you that I have this channel membership offer created for you that gives you some extra perks. And please check out the details in a video that is linked somewhere here. Alright, so let's get back to dedicated SQL Pool inside Synapse Analytics. So this is yet another component that we have available. And actually, we know quite a lot of components of Synapse already. So just to refresh your memory, it was like this. So inside Synapse, we have multiple parts, multiple components that are bundled under this Synapse umbrella, which should make this tool this one-stop shop for every BI and analytical needs. And the components that we covered so far were as follows. So we covered pipelines, and pipelines were basically used to ingest the data and to orchestrate the whole process. And then, as a part of pipelines, we have yet another feature, namely data flows. So data flows. And data flows, well, they can be used to transform our data in a visual way without writing a single line of code, this low-code / no-code tool. And basically pipelines inside Synapse is the same thing we have available inside Azure Data Factory. So that's the first component that we know. Then what we learned about were Spark pools. So let me write it down. Spark pools. And this component can be used to transform our data again, but this time by writing a code in one of those languages like Python, Scala, R, or SQL. And it gives us full flexibility and control over the code we write, way more than in case of data flows. And here you can compare Spark pools to a part of Databricks. So again, if you don't want to use Spark pools, go with Databricks. And so Databricks is the alternative, with asterisks, because Databricks is much more than just those clusters. And the thing that I want to cover today is the first flavor of SQL that is available inside Synapse, and namely this is dedicated SQL Pool, this relational data warehouse. But there are not foreign keys inside Synapse. So it is not relational per se, but you can think of it like this good old school classical data warehouse. So dedicated SQL Pool. Alright, so that's the topic for today. Now, if we think about the place where this component would fit into our design, our architecture, so it is like this. So here I created this beautiful drawing of our typical design, or design that shows various options we have when designing a solution. So let me quickly go through this. So as always, we have various data sources, files, databases, APIs, or whatever there is. This is the data that we have to process and then do something with this. And the first step that we do, well, is to ingest this data, to make it available inside Azure, just to grab it and dump to a data lake in its native form. And the place where it would be located is this first layer inside our data lake. And here I just called it raw layer. You can call it however you want. And we can use various tools to perform the ingestion part. We can use ADF pipelines or Synapse pipelines, the same stuff. Both of them are a very good choice to make the ingestion. In some cases, when none of those tools can work, for example, to get data from SharePoint, we could use Logic Apps. So that's the ingestion part. And then, once the data is dumped into our data lake, we have to start processing it. We have to start transforming it, to clean it, to remove duplicates, remove nulls, handle data quality issues, apply business rules that we got from the business. So basically, we have to transform it. And by transforming the data, I mean modifying it multiple times, just by reading it from a data lake, doing something with it, and then saving it back to a different layer into a data lake. Until finally, we have this nice dimensional model, facts and dimensions, stored in the last zone of our data lake. And obviously, we want to use Delta format, because it gives us those cool, nice features. And when it comes to number of services we could use, or types of services, we could go with Databricks, a very good choice. It works like a charm. We could use Synapse Spark Pool. If you would like to stay within the same service, then that's the solution here. Or if we prefer to transform our data visually, we could go with data flows that are available inside both Data Factory pipelines and Synapse pipelines. Great. So finally, once we end that transformation phase, we have our data here inside a data lake. Great, but then how to read this data, how to connect to it? And now those modern tools, well, they will be able to connect to a data lake and read Delta format without any issues. So case closed. But there might be many other solutions, older ones that you still have to support, that you have to feed with data, and they don't have a clue what a data lake is or what a Delta format is. Please remember that Delta, it has this Delta log that determines which files are valid in which version. So we cannot just read all Parquet files because we'll have invalid data. Or maybe our data lake is quite old and we don't use Delta format. Maybe we use Parquet or even CSVs. And I saw such kind of data lakes. And then we might want to grab this data from data lake and move it to this data warehouse, a database. And why database? Because basically every tool out there that would like to consume data, it can speak SQL. So if we make our data from data lake available by using SQL endpoint, that's great because everyone should be able to connect. And that's where dedicated SQL pool can be used. So actually, let me draw it on our diagram where this dedicated SQL pool fits. So it is yet another stage after ingestion and after transforming. So here we have our relational data warehouse. A relational data warehouse. And actually, if you take a look at this, you should remember this idea of having this extra data warehouse from one of the first episodes when I was talking about the evolution of big data architectures. And this one was called modern data warehouse, when we have some database after our data lake. And the goal here is to store our data in a tabular form, just like tables and columns, like in a regular good old school database. And it would be usually modeled as star schema or snowflake, because we want our data model to be simple and easy to understand by end users. And to make this work, we would simply have to copy the data from a data lake to our data warehouse. Obviously, it has some issues, like we have data into places, the same set of data. We have to maintain security in both places. We will pay for both services. But sometimes that's a good approach. And to provision this relational data warehouse based on this diagram, we would use this flavor of Synapse that I want to talk about today, this dedicated SQL Pool. Alright, so one more time. Dedicated SQL Pool is just this huge database that speaks SQL that is used to store your data and then serve it to your end consumers. So actually, we could call this layer serve or store and serve. Alright, so that's where dedicated SQL Pool comes in handy. Now, a very important thing about dedicated SQL Pool is to understand its architecture, because it is not a typical database like Azure database, Azure SQL database, or SQL Server. No, it uses this concept of MPP, strange abbreviation, but it simply means massively parallel processing. So let me write it down. Massively parallel processing. Which means that data is somehow processed in a parallel, right? That's the middle part. And we also have this massively part, which means that, well, dedicated SQL Pool is intended to be used with huge amounts of data. Really, big data. But not only big data in terms of different types of sources, no, by means of amount of data. And somewhere I remember I found a guideline to use dedicated SQL Pool if you have more than 1 terabyte of data. So really a lot of data. If you have less, then don't even bother starting with dedicated SQL Pool, because you will not benefit from it. And just a regular Azure SQL database should be enough to handle your workload. So really, use dedicated SQL Pool only if you have a lot of data, huge amounts. So for sure, for our replicable dataset, it's an overkill. We don't want to, or we don't have to use this type of service, but we will, just for learning purposes. All right, and once the data is loaded to data warehouse, this dedicated SQL Pool, well, it would be simply made available to some applications or users that would connect to it using TSQL, Transact SQL queries. So the way that basically everyone knows and can use. All right. Now, this MPP stuff and the architecture of dedicated SQL pool. And now pay attention, because it is really important to understand how it works under the hood, how it is built. Because if you don't pay attention, then you can very easily kill the performance of your dedicated SQL pool. And we don't want to do this. All right, so how does it work? So let's assume that I am this nice red guy. Actually, let me draw a smile to the face of this person. So let's assume that I want to run some query on my data stored in data warehouse. I want to run some select statement. Maybe I want to calculate total sales amount by customers. And what I will do? Well, I will connect to this endpoint exposed by dedicated SQL pool and simply send my SQL query. And under the hood, it is like this. So there is an endpoint exposed to end users applications. Actually, let me move this to the side to have a little bit more space. All right. And this black box here in the middle, this is our control node. This is our brain. This is our entry point to the whole dedicated SQL pool. So let me give it a name of control node. Our brain. Because it orchestrates the whole work that is done by SQL pool. And me as end user, me as the end user, I interact only with this control node. So my query is sent to it. I don't even know how it is then split later on, and you will see in a second that it has some additional components. So basically, I send my TSQL query like select statement. And I want to get my data fast. And I know that there is a lot of data in my data warehouse. That's why we are using the dedicated SQL pool, because I know that it works very well for these huge amounts of data. And I'm still smiling because I still hope that it will be fast. I will get a result in a fraction of seconds. Now, what control node does? Well, it doesn't do the work on its own. No, it distributes the workload into one or more compute nodes. So let me add those additional layer of compute power to our diagram. So we have compute nodes, those additional black things, and we can have between 1 to 60 compute nodes. And obviously, the more compute nodes we have, the faster, the more powerful our data warehouse will be, and at the same time, the more expensive. And guys, dedicated SQL pool can be very expensive, so pay a lot of attention if you're going to practice this on your own, because it might be painful when you see the bill. So those black things in the middle, these are compute nodes. And basically, this compute power, it runs our queries. It executes my query that I sent to dedicated SQL pool. And the control node, well, it simply distributes this work into those compute nodes. Compute nodes then run my query, each on its own part of the data, and send it back to the control node, which aggregates the results and send them back to the user, to me, in a fraction of a second, hopefully. And now we can have between 1 and 60 compute nodes. Depends how much we want to pay. and depends how much compute power we need. And there is a setting that I will show you in a second that determines number of compute nodes. So this was the compute power that is available inside our dedicated SQL pool. But obviously, apart from compute power, we also need the data. That's what data warehouse is all about, to store our data. Which means that we need to have some component that stores the data. And this part is called distribution. And we have exactly 60 distributions. No more, no less. Always 60 distributions. And this number is fixed, it cannot be changed. So 60 distributions. And basically our data that we store inside dedicated SQL pool is split somehow into those 60 distributions. We can have impact on the way it is split, and this is super important. It will be covered in a second. Because if we don't pay attention to this, we might kill performance of our warehouse. And basically, the service that is used to store the data, well, it's storage account or storage accounts. We don't see them, it's hidden from us, but we know from documentation that, again, Azure storage is used to host our data. But we don't see this. For us, it is just a database. And now, the important thing is that depending on the number of compute nodes, between 1 and 60, each of them will be associated with specific number of distributions. So if we have a single compute node, well, it would have to work with those 60 distributions. And you can think of those distributions like if you had 60 separate databases. So it would be the best if you could run your queries independently in parallel at the same time on each of those distributions. But to make it happen, you have to have multiple compute nodes. That's why you might want to pay more to have the results faster. So in the worst case, in the cheapest case, there is only a single compute node that has to work with all your data, which means that there won't be many parallelism involved. But if you pay more, or as you pay more, and you get more and more compute nodes, you will end up with a situation where a single compute node would have one or more distributions associated with it. In the most expensive case, the most performant case, you will have 60 compute nodes, which means that every compute node will have to work with its dedicated distribution, with only one, which would be the fastest option, right? Because each compute node will have the smallest part of data to be processed. But of course, that comes with a price. If you have less than 60 compute nodes, then it might be the case that, well, a single compute node will work on 3, 4, or 5 distributions. So it will have more data to process on its own, which will take more time. But if you don't want to pay tons of money, maybe that's a valid option. And now, the important thing is that this link between compute node and distribution, this association, because ideally, what we would like to have is a situation when the query that is sent to the specific compute node can be satisfied with the data that is stored on its associated distribution. Because if that's the case, then this compute node has all the data it needs to answer your query. And in a second, you will see what you can do to arrange your data in this way. But unfortunately, it is not always possible. And you might have cases when your compute node, it will need data from its own distribution, but also from some other one that it is not associated with it, which means that at runtime, this data from this additional distribution would have to be moved to this compute node to be made available to it. And this process, as you can guess, it takes time. And it is a performance killer for your queries. And you want to avoid this by arranging your data correctly. We'll do this in a second. And this process of data movement that we want to avoid is called, surprise, surprise, data movement. And that's something that we want to avoid. So data movement is bad. No, we don't want to have this inside our dedicated SQL pool. Data movement. And you can also find a name, data shuffle. The same stuff simply means dragging the data from one distribution to a different compute node. Data shuffle. And basically, if your query executed on dedicated SQL pool is painfully slow, then the usual suspect is data movement, because your data is not stored in the optimal way. Now, I told you that we can have between 1 and 60 compute nodes inside our dedicated SQL pool. So what determines this number, this power of our control node? And basically, this is something called performance level. So let me explain how it works. So when we are creating a dedicated SQL pool, and I will do this in a second, we can select this initial performance level of our warehouse. And obviously, the more powerful it is, the more expensive it is. Later on, we can change it. We're going to scale it up to have more compute nodes, or scale it down to have less, depending on our workload. But at the time when we are creating the dedicated SQL pool, we have to make some initial choice. And this choice, or this property, is called performance level. Performance level. Unfortunately, it doesn't mean that if you choose the best performance level, it doesn't mean that your query should be super fast. No, if you don't pay attention to the data distribution, it can still be slow, even that you are throwing a lot of money into it. So you have performance level, and it directly translates to number of compute nodes that we have available. So compute nodes. All right. And now the cheapest option that you can choose has this nice name of DW100C. It explains everything, right? And as a result, you will get a single compute node. So very cheap, very slow version, but for training purposes, it might be fine. Then there are multiple levels that you could choose in the middle, and you can end up with the most expensive version that is called DW30,000C. Like so. And in this case, you will have exactly 60 compute nodes, the most powerful version, where every compute node would have only a single distribution it works with. So it should be the fastest one. Now, the thing is that this service in general might be expensive. especially in case of these high performance levels. So let me now create a new dedicated SQL pool, and let me show you when and where this performance level can be set. So let me jump into Azure portal, and that's the Synapse workspace that we've been working on recently. And I will open Synapse Studio, and here I will create a new SQL pool. We already have something called the built-in pool of serverless type. We'll cover that in a future episode. But what I want to create today is a dedicated SQL pool, not a serverless one. So let's click on this new button. Let's give it a name like my test data warehouse. And here you can see this performance level slider. So that's the place when you can choose how powerful your data warehouse will be. And also, please pay attention to this estimated price. And here the price is set per hour, not per month, per hour of your warehouse up and running. So in this default mode, it is 14 euros per hour. In the cheapest version that we'll use, it is like €1.5 per hour. In the most expensive one, it is over €400 per hour. So very quickly it might be a significant part of your bill. So let me decrease the power. I will have only a single node, but that's fine. The most important part is that it will not be super expensive for me. And let me create this. I will go with the default settings for the rest of them, and let me just wait a few minutes for this my test data warehouse to be created, and then I'll be back. Alright, so my test data warehouse dedicated SQL pool has been created and is online. And here, once you are done with working with this pool, make sure to pause it by using this button, pause, because once you pause the poll, you will stop paying for it. And unfortunately, there is no auto-terminate built-in dedicated SQL pool like we had in case of Databricks, clusters, or Spark SQL pools. Here, if you forget to shut it down, the bill will just keep getting bigger and bigger. So once you are done with working with dedicated SQL pool, please pause it or even remove it if you don't need it anymore. Now, if you want to work with dedicated SQL pool from Synapse, you can do this. That's fine, because the goal of Synapse was to provide this unified UI, which you shouldn't have to leave. So if we go to the data tab, so here we have right now this lake database that has our Piotr Tidimo lake database. So if I recall, yep, we have some minifigs here. And this lake database was a database which points to a data stored on a data lake. Right? So this data is not physically a part of Synapse. And if I refresh this, I should see a new database. Yes, I have this SQL database, this my test data warehouse. That's my dedicated SQL pool. This is this fully blown SQL database meant for huge workloads. And here I could just create tables, write queries, and work with data. If I prefer to work outside of this UI, that's fine. For example, I'm an old guy. I use SQL Server Management Studio whenever I have to work with data. And I would like to connect to this dedicated SQL pool from SSMS. And yes, this is possible. So I will go to my Synapse workspace, to the main page, and here I have this dedicated SQL endpoint. So that's the place to which I would send my queries, to the control node, to the brain. And I can use this address to connect to my pool from SQL Server Management Studio. So let me copy this address. And here I have my SSMS already opened. And I want to connect to a database engine. As a server name, let me paste the address that we got from Azure portal. And I will connect as Piotr and add table on azure.pl. So the same user that I've been using in Azure portal. And hopefully I will be able to connect. Of course, I have to authenticate. And that's fine. I've been authenticated. And in a second, yes, I connected to my dedicated SQL pool from my on-premises SQL Server Management Studio. And here I could just write queries and interact with database like as always did. So that's a way to go. And at the same time, it is a proof that indeed every tool that can speak SQL, it can connect to dedicated SQL pool. All right, but please remember about pausing the pool. If you stopped working with this, just pause it, just to avoid costs. Unfortunately, there is no place in the UI where you could define, I want to pause this pool, let's say at 7 p.m. No, you have to implement this on your own. Fortunately, you can find Azure functions that do exactly this, but it is on you to implement this and to remember to set it up. All right, so let's get back to our drawing, because I told you that the way we distribute data on distributions is super important. Why? Because we want to avoid this data movement. We want to make sure that the data that is needed by our compute nodes is stored on associated distributions. And yes, as developers, we can define rules that will be used to distribute the data between those distributions. And actually, we have 3 methods we could use to distribute the data. And let me quickly go through them. So the first method we could use is called hash distribution. So hash. And it works like this. So let's assume that we have some data that we would like to load into our dedicated SQL pool. So let's say this is our dataset that we want to load from a data lake to dedicated SQL pool. And in case of hash distribution, we usually do this in case of tables that has a lot of data, millions or billions of rows. So a lot of data. And it should give you a hint about a type of table that could be used, that should be used with this type of distribution. So in our dimensional modeling, which type of tables has a lot of data? Facts or dimensions? And obviously these are facts because they store the most amount of data. So let's assume that this table that we want to load to dedicated SQL pool is our sales fact table. Sales fact table. And let's assume it has billions of rows. Our enterprise is super profitable. We've got thousands of customers and we want to just analyze this data. All right. And let's assume that, well, our table, well, it has multiple columns. And let's assume that the first one, or one of them, is customer ID. It is our identifier of a customer, or maybe a key to our customer dimension. So this is customer ID. And obviously we have multiple columns inside our table, and let's say that the data is as follows. The first row is for customer 1, then we have data for customer 2, for customer 5, 1, 7, 5, 10, and so on. And we want to grab this data and distribute it somehow into those 60 distributions. And one more time, there are always exactly 60 distributions, no more, no less. So this is our target on the right hand side, those distributions. The first one, then the second one, and so on up to 60 of them. So these are 60 distributions. Alright, and the way hash distribution works is basically like this. We indicate a column or set of columns based on which Azure will calculate a hash value, and based on this hash value it will simply assign a particular row to one of those 60 distributions. So it will calculate some function, some value, some hash value, and based on the result it will decide to which distribution this particular row should be saved to. And this hash function, this hash distribution, is deterministic, which means that for the same input, for the same value of a specific column, it will always result with the same output. Deterministic. Alright, but what does it mean? Why should we care? So let's assume that you would like to hash our data based on this customer ID. And let's assume that it is like this. So the first row is green. I will use colors to make it visually attractive for you and to explain it in a better way. Then for this value 1, our hash function will be calculated, and it is done automatically by Azure. And let's say that for this value it decided to store this row inside the first distribution here. That's why I drew this green row in this place. Then we have a row with ID 2, and let's assume that for this value we got a different hash output, which resulted in storing this row in the second distribution. Then we've got a row with ID 5, and let's assume that it resulted in a hash output that assigned this row to the last distribution. Then we again have a row with customer ID equal to 1, so let me use the same color, and because our function, the hash function, is deterministic, which means that for the same input it will give the same output. So it will assign this row again to the same distribution that was assigned previously. So it will be like this. Then we've got a row with ID 7, so let's use yellow, and here let's say that it will also result in a distribution number 1, the first one. That's totally fine. Please remember that we have only 60 distributions, and fortunately we have more customers than just 60, which means that obviously we will result with the same distribution number for multiple customers. But for the same customer, it is guaranteed that its rows would be stored on the same distribution. So let's continue this exercise. So we again have customer. Oh, come on, wrong color. We have customer number 5, which was purple, and it would be assigned to the last distribution. And we have customer number 10. Let's use this light blue, and maybe it would be assigned, I don't know, to the second distribution, like so. So you should see a pattern already that rows with the same value of our column that we'll use for hashing will be stored on the same distribution. And this is important because that's the way we can guarantee that the similar data would be stored in the same place. Alright, but why should we care? So let me write some properties of this method. So let's assume that you would like to run a query like the one that I mentioned at the beginning. We have multiple customers and you would like to calculate a total amount by customer. So if we send this query to our control node, it will split it to multiple compute nodes, and it would be ideally if every compute node would have a task like, please calculate this aggregated sales amount for customer 1, 3, and 7 for the first one. The second one would do the same, but for customer 2 and 8. The next one for customer 10 and 12, and so on. And if we make sure that the sales transactions for the same customer are located for sure within the same distribution, it means that associated compute node would have all the data it needs. We would avoid this dreaded data movement, so it should be fast. And that's the reason why we should care about distribution. And the hash method, well, it gives us this advantage. Alright, so when should we use this? Well, first of all, it should be used for fact tables. For facts, not for dimensions, for facts, for those big ones, like sales transactions. Secondly, documentation says, well, if you have more than 2 gigabytes, then go with this hash distribution. But honestly, 2 gigabytes is not a lot of data, especially that we know that dedicated SQL pool is meant for those huge workloads. But basically, a rule of thumb for hash distribution is to use this for facts tables that are huge by nature. Then, alright, but which column should I use for this hash partitioning? And here the answer is, or the guidelines are simple, because they say, well, choose a column or set of columns that you know that are used inside join, on join conditions, or by group by clause. Like select sum amount, group by customer ID. That's why we used this customer ID as a hash function. Alright, great, but the problem is that at the time we are defining the structure of our tables, we might not know upfront what queries would be executed on them. And that's fine. This distribution can be changed later. It's not a simple operation, but it is doable. I will show it in a second. Alright, great. So are there any guidelines about which columns you should not use as this hashing function? And yes, the guideline documentation says don't use a date column like sale date. No. Why? Because you might end up with data from the same period located on the same distribution. Let's say sales data from the same month would be stored on the same distribution in the same place. And then if you would like to run some queries on this data, well, it would have to be handled by a single compute node that is associated with this distribution. So you wouldn't benefit much from this parallel processing, which is the idea behind MPP. So no, don't use date columns. But actually, date column is a very good candidate for a different performance optimization technique. And this technique, I will cover that in one of future episodes. It's called partitioning. And this is a different partitioning that we had in case of data lakes. But we'll cover that separately. All right, so that's one thing. Secondly, when you are choosing a column to be used for this hash distribution, you should pay attention to data distribution, because if you don't, then you might end up with most of the data stored on a single distribution, which again is not desired. So let me explain what I mean by this. So let's assume that this is a diagram that shows customer ID like 1, 2, 3, 4, and so on. 1, 2, 3, 4. And on the second axis, you would have number of sales orders made by this particular customer. And you might have a case like this. So the first customer made this number of orders, the second one made this, then this one made this, but the last one, or set of them, have a totally different number by the means of scale. Maybe the customer number 4 is our main customer, and it produces most of our data. So we have a data skew because our distribution is not unified, is not uniformed. So if we use a customer ID as our hash column, it means that 90% of our data would land in a single distribution, which again is not desired, because the single cluster that will work on this distribution will have a lot of data to be processed, and we want to distribute it more or less evenly, so each of our compute nodes would finish more or less at the same time. So pay attention to this data skew. And again, at the time you are designing your tables, it might be difficult to guess what the distribution will be in the future, in 1 year or so. So just take your guess. Or if you know your data already, maybe you might take an educated guess. Or if there is no way you could select a proper column, you could combine multiple columns. So you could use multiple columns for this hash operation. So this way you might distribute it a little bit more evenly. All right, so that was those watchouts for hash distribution. And when it comes to indexing, and in a nutshell, indexing in databases is a method to increase performance. Simple as that. Here, for this type of distribution, for hash distributed tables, basically for facts, you should use clustered column store indexed. Clustered column store. Index. And without going too deep into details, column store indexed is something similar to what Parquet and Delta does. It organizes your data physically in columns, which gives some advantages when it comes to analytical queries like the ones that we run on our data warehouses. But again, there is an additional recommendation to use this type of index only if you have more than 60 million rows. Why? again, it comes down to the way column store index work. To make them efficient, to use their full capabilities, they have to be compressed. And to make a segment of the index compressed, it has to have at least 1 million rows. And because we have 60 distributions, that's why our table should have at least 60 million rows to give some benefits from this type of index. All right, so let's jump to Azure portal, to our dedicated SQL pool, and let me create a table that will use this type of distribution. So to make this work, I will go into Develop tab, and here, well, previously we used this place to create our notebooks. Right now, I will just create a new SQL script. So, new SQL script, let me indicate that I want to run my query on my test data warehouse on this dedicated SQL pool that we just created. And let me copy some SQL code that will create a table. So first of all, let me create a schema called replicable. And schema, well, it will just allow us to split our data logically into multiple areas. And then I will create a table called replicable minifix. Here we've got just a definition of this table, what columns it should have, what data types, what constraints it will have. And here, that's the important part, because that's where you define various options. So first of all, I want to use clustered column store index. And secondly, I want to distribute my data by using hash distribution method. And the column that I want to be used for this hash operation is my set number column. And now, if you think about those recommendations I gave you 10 minutes ago, you will quickly notice that minifix, well, it is not a fact table, it's a dimension. It is a small table, so we shouldn't be using this hash distribution method. And yes, you're right. In a real life, we wouldn't be using this method. We wouldn't be using Synapse dedicated pool in the first place, but it is just for education purposes. So let me create this table, and hopefully it will be created. And yes, it was created. And if we go back to our data, I should see a new table. Let me refresh the view, and there it is. We have this replicable minifix table created. Just a regular table. And the same should be visible from Management Studio. Let me just refresh it. And there it goes. We have our table created that uses this hash distribution method. Great. So that was the first method we could use. All right, so what are the other options? So the second method is called round robin, and it works like this. So round robin. Round robin. And it works differently to hash, because it is like this. Let's assume again that we have some data that you would like to load inside our table in dedicated SQL pool. So this is our source data. And again, we have those 60 distributions. No more, no less. There are always exactly 60 distributions, and you cannot change this. So those are distributions. 60. All right. And it works like this. So again, we want to distribute the data somehow into those distributions. And now let's assume that, well, we have the first row, the green one. And round robin method works in a way that the first distribution is chosen somehow. Let's say that this row was assigned to the first distribution and it is saved there. Then we've got yet another row inside our source data, and then the next row is saved to the next distribution without any additional logic. Simply go through every distribution and split our source data evenly, one by one. So we would go like this. We have multiple rows and they will be simply assigned to every distribution, one by one. There's no additional logic included. Alright, so let me write the most important information about this type of distribution. So when should we use this? What are the benefits? Well, simply put, this is the fastest method of loading the data. Because we don't have to calculate this hash value, or Synapse doesn't have to calculate this, which means that we can just dump the data or insert the data as fast as possible. Alright, but in what cases we care that much about the insert speed? And the answer is simple. In case of staging tables. So staging table. And staging tables is a concept inside databases when we have a dedicated set of tables to which we just dump the data as fast as possible. Staging tables are not the final tables. No, they are just used as a temporary place to which we load the data. And later on, we would grab the data from the staging tables and add them or use them to insert to final tables, insert or update. So that's the way to add data to your database as fast as possible. And in those cases, a round robin distribution is the suggested one. And actually, it is also a default option. So if you don't specify any distribution explicitly when you are creating your table, then this round robin version will be used out of the box. And when it comes to indexing, again, speed is our priority, usually when we choose this type of distribution. And in this case, to make it faster, we don't want to have any indexes at all, which means that we'll go with a heap. And heap simply means no indexes. All right. Now, obviously, for the insert phase, that's fine. Later on, when we'll be selecting data from this table to insert them to final tables, we might want to have some indexes. But this will be done later. So once we loaded the data to this round robin distributed table, then we can add additional indexes. All right, and how to create a table that would use this distribution method of round robin? Well, or maybe we made a mistake. We have this replicable minifix table and we used hash method, but we know our command is said it's not a fact, and maybe I would like to change it to use round robin. The thing is that we cannot just alter a table and change its distribution method. No, it's not supported. So the way to go is to create a brand new table with proper distribution method and simply populate it with data from the original table. And that's how we could do this, by using the following syntax. So let me explain what I'm doing here. So I'm creating a brand new table, this minifix round robin, with proper distribution this time, or round robin, And here I'm not specifying its structure. No, I simply tell just grab all data from this original table and use it as a source for this new table. Now, at this moment, my original table is empty, so no data will be available in the new one. But in real life, that's how you would do this. And we should have a new table created, this replicable round robin, and you can see a different icon. This one indicates or suggests this round robin distribution, that you go one by one by various distributions and add rows there. Then the thing is that now we have two tables, right? Minifix and minifix round robin, and maybe we would like to keep using this name. So how to do this? Well, once your data is copied, you would simply drop this table, and then rename this table. So that's how you could make this work. All right, so this was a round robin, default one, the fastest option to be used basically with staging tables. All right, and there is the final option, the third one, that is called replicated. So let me explain how it works. So replicated. All right. And in this case, we again have some source table that you would like to load from a data lake to our table inside Synapse Dedicated SQL Pool. So we have again those 60 distributions always. 60. And we want to distribute our data somehow. And this replicated mode means, well, simply create multiple copies of our data. So let's assume that we have this green row in our source data. If we use replicated mode, this row would be inserted to every distribution. And the same with all other rows. We will simply have multiple copies of our data. Like so. Alright, great, but when should we use this? And why? Why do we want to have our data copied? We will pay more for storage, right? So what's the point of doing this? And yes, it's true. But the thing is that, well, again, that's our architecture. And usually, when you run your queries on your data warehouse, you join your facts with dimensions. And probably you want to avoid this data movement, and those dimensions, they will be needed by every compute node, because every query will use them. So to avoid this data movement, let's just replicate our dimensions on every distribution. So they will be available to every compute node. So no data would have to be copied. And that's why you might want to use this replicated distribution type. So yes, the recommendation is to use this type of distribution for dimensions. Because you want to make them available for every compute node. And obviously, dimensions, we will have multiple copies. And my whiteboard is not very responsive. Maybe too many lines. Anyway, the goal here is to make this table available on every compute node, and it is to be used with dimensions. But please remember that, well, if you replicate the data on 60 distributions, you might end up with a lot of data. And the recommendation is to do this for tables that are smaller than 2 gigabytes, just to avoid this excessive data multiplication. And that's how you can impact the way your data is stored inside those distributions. First, to make your queries faster by storing the data in a place that will be instantly available to your compute nodes. Alright, and before we finish this episode, let me pause my poll, because I don't want to pay too much for it. So let me go to my test data warehouse, and yes, please stop it. Alright, so to summarize, Dedicated SQL Pool is a part of Azure Synapse Analytics. And that's the good old-fashioned data warehouse that has tables and columns. That's the place to which you would load your data and make it available to consumers by using SQL queries. The watchouts are that it might be quite expensive. It is to be used with very big datasets. Forget about using it for small databases. There is no point in doing this. And secondly, if you start to use Dedicated SQL Pool, then pay attention to its architecture and to data distribution, because if you do it wrong, then data would have to be copied live during the query execution just to make the data available for compute nodes. And to make it better, you can use 3 distribution methods: hash method, round robin, or replicated. And hash simply it means I'm selecting a set of columns or a single column based on which a specific row will be assigned to a specific distribution. And this way I can enforce that, for example, data for the same customer will be stored on the same distribution. Then we've got round robin, which simply means, well, I just want to distribute my data evenly on every distribution. But I don't really care where my row will land. I don't care about this. I just want to load my data as fast as possible. And this method is used basically for staging tables. And the last option is replicated distribution, which means that you will have multiple copies of your data. And it is recommended to be used together with dimensions to make this data available on every compute node without data movement, which is bad. You don't want to have data movement. Alright, and this is it. And see you next time. Take care.